Hi everyone, this is Professor H. Rahman from Agriculture and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL course on traction engineering. This is lecture 19 where I'll try to cover tractive performance prediction models developed by Brixius. As I said, the theoretical derivations which we did for calculating the tractive performance of pneumatic wheels, we need to know the stress distribution, we need to know the shear displacement, we need to know the relationship between shear stress and shear displacement, and the distribution of normal pressure. So, these are all theoretically it seems very sound, but actually it is very difficult to get all those informations. Hence, some equations have been developed. A set of equations I discuss in my lecture 18. Now, I will develop the most recently or commonly used equations which have been developed by Brixius. There are plenty of equations available, but these are the two Wismer and Luth and Brixius equations. These are the most commonly used ones. That's why I tried to discuss in detail about those two equations. So, in this lecture, I will try to cover about Brixius equations, where I will cover the concepts of mobility number, concepts of motion resistance ratio, torque ratio, and effect of tire, soil variables and tractive performance. So, Brixius, look, we have already discussed about Wismer and Luth's equation. That's why Brixius wanted to modify that equation. So, what he did is he tried to take data obtained from 121 tire soil combinations. Look at the numbers: 121 tire soil combinations in 2,500 field tests. So, there is a huge amount of data. Based on those data, he tried to develop some equations. So, he tried to identify what are the parameters which are affecting the tractive performance, and then he tried to develop some equations with respect to your COT, torque ratio with respect to motion resistance ratio, and from there he derived the coefficient of traction and tractive efficiency. So, he identified 11 parameters, okay, and he grouped them into soil, wheel and system parameters. Under soil parameters, he took cone index, and under tire, he took tractor section width, overall tire diameter, tire rolling radius, tire section height, tire deflection delta. And here I have indicated the symbols CI, B, D, R, H and delta and the dimensions. Okay. Now, the system parameters are your vertical load which is coming on the wheel, then the motion resistance, towing force, wheel pull, wheel torque and wheel slip. So, these are the parameters he identified, 11 parameters. He then applied dimensional analysis technique, that is Buckingham's pi theorem. So, that means 11 minus 2. So, that should be 9 dimensionless ratio variables. Out of these 9 dimensionless ratio variables, he identified as wheel numeric CIBD upon W, width to diameter ratio B upon D, that means section width to wheel diameter, deflection ratio del upon H, rolling radius to diameter ratio R upon D, section height ratio H upon D, that means section height by overall diameter, slip, torque or gross traction ratio Q upon RW, motion resistance ratio M upon W and pull ratio as P upon W. So, these are the 9 dimension ratio variables he identified. Out of these 9 dimensionless ratio variables, he found out 2 ratios which can be derived from other ratios. For example, P by W. can be derived if you know Q by RW, if you know M by W. So, the difference of these two will give you P upon W. Similarly, H upon D, section height ratio, that can be derived if you know the rolling radius R and if you know the overall diameter and del by H ratio. So, these are the two parameters P by W and H by D. They are derived from the two other dimensionless variables which he identified. The other thing is the rolling radius to diameter ratio is nearly constant for agricultural tractor. Hence, he said it can be neglected, and that's what Wismar and Ruth did. So, R by D ratio is nearly equivalent to 0.475 for whatever combination of tire soil he has tried. So, that means the rolling radius ratio is nearly constant, hence he neglected that one. So, out of 9, then you take minus 3, 1, 2 is the dimension ratios which are derived from others. The R by D also he took as constant. So, remaining are 6 dimensionless ratio variables. So, he defined one terminology Bn, which is called mobility number. Okay. So, Bn is mobility number. This is equal to wheel numeric CIBD upon W. Then he has added two things, del by H ratio and B by D ratio. Okay. So, 1 plus into 1 plus 5 del by H by 1 plus 3 B by D. So, that together is called mobility number. Whereas Wismar and Ruth, he defined wheel numeric, only he has taken CIBD upon W. These two components he has not considered, he has taken as a constant. Okay. So, this is the advantage we can say. So, we will see what is the advantage we are getting later on. Then the equations which he developed is torque or gross traction ratio. This is written as Q upon RW. Q is the torque and R is the rolling radius, W is the dynamic weight. So, in other words, you can write F by W, that means tractive force divided by the dynamic load, that is equal to 0.88 into 1 minus e to the power minus 0.1 Bn into 1 minus e to the power minus 7.5 S plus 0.04. Let us now see what is the significance of these terms which are included in this equation. The first is 0.88. What does it show? So, it shows or limits the maximum torque ratio to 0.92. 0.88 and 0.04. If you add, that becomes 0.92. That means 92% of the torque is converted to its full power. Okay. And where it is obtained? This is obtained with a large mobility number at high slip value. These are the two conditions. That means you will get 0.92 when there will be large mobility number and when there will be high slip. Then the second important component is your mobility number, e to the power minus 0.1 Bn. That's mobility number here controls the maximum thrust which is developed, and it is developed at a higher slip. Okay. The torque ratio increases with increase in mobility number. Okay. Torque ratio increases with increase in mobility number. Now, the second important term is this e to the power minus 7.5 S. The constant 7.5 is called the gripping or surface factor. It controls the rate of rise of torque ratio curve with slip. Okay. And the factor is smaller for wet surface and it is larger for stacked wheels. Now he developed another equation, before that, 0.04. What does it reflect? It reflects the torque ratio at zero slip, irrespective of what cell condition. If torque ratio is at zero slip is 0.04. So now let us see what is the equation which is developed for motion resistance ratio, which is denoted as rho, and this is equal to m upon w, and that is equal to 1 upon Bn plus 0.5 S by square root of Bn plus 0.04. So let us now see how the motion resistance ratio is varying. Why there is a rolling resistance? First, if you know, then only you can justify this nature of the curve. The motion resistance ratio of a pneumatic wheel is because of so many factors. So if you like to identify those factors, the first is the tire flexing and scrubbing. Tire flexing and scrubbing. The second one is due to compaction of soil. Third one is due to bulldozing. Then fourth one is due to lateral drag, which is caused because of soil adherence to the tire. So these are the four reasons for which there will be motion resistance. In a hard soil, basically it is the tire flexing and scrubbing which will create the motion resistance. So now after knowing this, then next thing is what are the terms which are used in this equation, motion resistance equation, motion resistance ratio equation. The first term is 1 upon Bn. So what does it indicate? Bn is in the denominator. That means higher the value of Bn, lesser will be the rolling resistance. As Bn decreases, MRR, motion resistance ratio increases. So Bn decreases means Bn could be due to decrease in soil strength, due to decrease in deflection ratio, due to increase in width to diameter ratio. These are the factors by which you can decrease the Bn value. Since Bn value is in the denominator, so that's why 1 upon Bn will give you higher rolling resistance ratio. Now the second term is 0.5 S upon square root of Bn. If you look at this one, motion resistance ratio increases with slip due to increase in tire sinkage and soil shearing. Okay, so more the slip, more will be the rolling resistance. Now the third component is your 0.04. This value represents the motion resistance ratio on a hard surface, and it represents the minimum value on any surface. Okay, this is basically due to tire flexing and scrubbing. Now once we know the equations which are developed for torque ratio, which is nothing but the coefficient of gross traction, then we knew the equation which is developed for motion resistance ratio, and the nature of the motion resistance ratio curve we can see with increase in mobility number we are getting lesser and lesser motion resistance ratio. That means with increase in CI, with increase in del by H ratio, we are getting more mobility number, and then we are getting lesser motion resistance ratio. Then he derived coefficient of traction and net traction ratio, which is P upon W, there is the difference between Q by RW minus M upon W. Okay? And then he tried to plot NTR versus fuel slip for different BN values, starting from 5 to 80. So, BN value increase means your coefficient of traction increases for the same slip. If you look at 0.3 or 0.2, wherever you look at, all the cases will find that the COT value increases with increase in BN value, that is fuel numeric value. Why it is so? BN value increase means the soil is hard, so there is lesser rolling resistance, hence the power which is supplied to the tractor wheel or to the single wheel, that will consume less power to overcome the rolling resistance, hence more power is available as useful power. Next thing is tractive efficiency. Once you derived motion resistance, coefficient of traction, then we try to find out what is the expression for tractive efficiency. The expression remains same, that means output power by input power, and it is a function of slip. So, P into 1 minus S by Q by R. So, we have divided W to find out this is COT and the other one is your torque ratio. Okay. Now, the nature of the curve we can see from here. The variation of TE with fuel slip is shown in this figure. When the fuel slip is less than 5%, okay, what happens? A large portion of the power is required to overcome rolling resistance. If fuel slip is more than 20%, beyond this, again it is going down. Tractive efficiency, if you look at the cursor, it is rising to a peak very sharply, then it is going down. So, if you are beyond 20% or 25%, then there is again decrease in tractive efficiency, and that decrease in tractive efficiency is because of increasing portion of input power which is lost due to slippage. Okay. If the slip is less than 5%, there is loss. Most of the power is used for overcoming the rolling resistance. If it is more than 20%, if the slip is more than 20%, most of the power is lost because of the wheel slip. So, we have to operate in between these two so that we can get maximum tractive efficiency. Now, if you try to plot tractive efficiency versus slip and pull versus slip, that will give a better picture, in the sense the nature of the curves are different. In case of a tractive efficiency curve, it reaches to a peak within 10%. If you look at when the wheel is hard, the mobility number is high from 20 to 80, then you can getting a maximum value within 10%. Now, if the mobility number is 10, then we are getting maximum value around 15%. If the mobility number is 5, then we are getting a maximum value around 25% slip. Whereas at these slip values, if you draw vertical lines, so at these slip values, the COT curve, that is coefficient of traction curve, or the pull to weight ratio curve, is not giving the maximum value. So, maximum value you can see you are getting somewhere here. In case of wheel numeric mobility number 5, in case of mobility number 10, you are getting maximum here. In case of 20, you are getting here. Sorry, in case of 10, you are getting here somewhere. So, that means the slip at which you are getting maximum tractive efficiency and the slip at which you are getting maximum pull, they are not matching. So, if you want more pull or if you want more tractive efficiency, that we have to first find out, or you have to make a compromise so that we will get more pull, at the same time more tractive efficiency. We cannot say maximum, but we can say we can get more pull and more tractive efficiency. So that's why a design curve has been drawn here, which is shown by the green line. So depending on our soil condition, we have to find out which slip should be followed in the field so that you will get both maximum tractive efficiency and more pull. So if you look at this curve, so you are nearly, when the soil is hard, that means when the mobility number is 80, we can see we are reaching to a peak here, and when the mobility number is 40, we are reaching to a peak here. When the mobility number is 20, we are reaching to a peak here. So these design curves are basically for higher tractive efficiency, but the pull which you are getting is at 20, this is the pull which you are getting. At 40, this is the pull which you are getting, and at 80, this is the pull which you are getting, which is less than the maximum pull. So now this suggests that there should be a design curve taking into account which thing we like more, tractive efficiency or we like more pull. So these are the sets of equations which we discuss. One is for Wismar and Luth, the other one is for Brixius, and let us see now the applicability of Brixius equation. The applicability of Brixius equation is for a cone index starting from 100 to 5000. The very high value, 100 to 5000, and the B by D ratio is 0.18 to 0.9. That is the range. Del by H ratio is from 0.08 to 0.32, and R by D ratio is almost constant, 0.475. And if you like to compare with Wismar and Luth, then there is no indication for cone index value. What is its applicability? Only the limited value is B by D ratio is only 0.3. If we exceed this value, what will happen? He has not mentioned, neither nobody has tried to find verify this. And del by H ratio, if you look at it, is 0.2, and R by D ratio for agricultural tires, it is nearly 0.475. But the advantage which Brixius has done is the maximum value has increased to 0.92 times. Okay, whereas the tractive effort which is developed by Wismar and Luth is only 0.75. So that is the difference. And in Brixius equation, he has considered both deflection as well as B by D ratio, which Wismar and Luth equation has not considered. The third thing is, in case of a rolling resistance ratio, in case for Wismar and Luth equation, there is no difference. You cannot differentiate the rolling resistance of a towed wheel or rolling resistance of a powered wheel, because slip factor was not there. Whereas in case of Brixius equation, he has considered slip factor. So that's why Brixius equation is much better. These equations are much better, and it has more applicability as compared to Wismar and Luth equation. So one more thing I like to add here is these two equations, these two the scientists with Brixius as well as Wismar and Luth, both have developed equations for bias ply tire. Applicability of these equations which we discussed for radial ply tires is not known. Rather, Brixius has indicated that you can change the coefficient values so that it can be applied to radial tires. Some of the suggestions what he has given is, you can change the value of constant 7.5. The equations, let me go back to the equation, there it will be better to so what changes he has suggested if you are interested to find out or apply this equation to radial tires. The first suggestion he has given is this 7.5. He suggested that instead of 7.5, we can try with 8.5 to 10.5. Okay, and the constant 0.04, he said it should be 0.035 or 0.03, that is the range. And the term 0.1 should be converted to 0.88. These are some of the suggestions, and in the motion resistance ratio, he also suggested a change in the terms of, instead of 1 upon Bn, he suggested it should be 0.9 upon Bn. These are some of the suggestions given by Brixius to apply these equations to radial tires. So, nevertheless, Brixius equations are better in the sense it takes into account the slip, it takes into account the del by H ratio, it takes into account the B by D ratio. So, these are some of the advantages of Brixius equation. Okay. So, that is why now ASAB has recommended this in the standard. We will find ASAB standard, will find these are the equations which are available for predicting the tractive performance of tires, pneumatic tires. So, in summary, I can say I tried to discuss the equations which are developed, and for developing what are the dimensionless ratio variables which are considered, those are also discussed. Then we discuss finally the applicability of these equations, and then we compared Brixius equation with Lewis equation, and what are the modifications which can be incorporated in the developed equations, so that the equations can be applied to radial ply tires. That's all. Thank you.